Example 12.6 is an adiabatic expansion, and the goal is to use the adiabatic pressure versus volume relationship, that is PV to the gamma equals constant, to find a change in the pressure and the work done on a gas. So a monatomic ideal gas, degrees of freedom equals 3. At an initial pressure of 101,000 pascals, so P sub naught equals 101 kilopascals, expands adiabatically from an initial volume of 1.5 meters cubed. V naught equals 1.5 meters cubed, doubling its volume, so V final is 3 meters cubed. Find the new pressure. So we're going to use the new pressure is going to be P equals, P sub naught, V sub naught to the gamma over V sub final to the gamma. That's going to be our final value. Gamma is degrees of freedom plus 2 over 2. So in this case it is 5 thirds. Sorry, degrees of freedom plus 2 over degrees of freedom. So it's 5 thirds. So we're going to plug in numbers of since it's V naught over V final, both of those are to the gamma power. I can actually pull the gamma out and just do that once. So it's 101,000 times 1/2 to the 5 thirds. So it comes out to be 31,813 pascals. Now they say sketch the PV diagram and estimate the work done on the gas. Now, in order to do that, look here at 1.5, a volume of 1.5. If you look up there along that path, you will see that says 100 kilopascals, basically. That would be P sub naught. Then at 3 pascals, you can look and should have 31,813, so about 32,000 pascals. So here's 0.3. 32,000 would be just a little bit above 30,000, so there's our 32,000 pascals. And then you should find some middle value at 2, and if you wanted to do 2, you would do 101,000 times 2 thirds to the 5 thirds, and that comes out to be... Okay, how long have I been talking without the recording button going? This might be a repeat of myself, but let's go ahead and say it anyway. We have here, this point is what we were given at the beginning. The initial pressure was 100,000 pascals. The initial volume was 1.5 cubic meters. Then we have this point that we calculated, 101,000 times, or we have 31,800, which is about 32,000 pascals, or 0.32 times 10 to the 5th, and that's at 3 meters. Then we need some kind of middle point, so just plug in 2 thirds to the 5 thirds, because what was I saying? Oh, right, because it's 2 meters cubed over 3 meters cubed. Actually, we're using the initial pressure, so we need to use that initial volume of 1.5. And then we divide that by our final volume. Here, where our final volume is 2. So plugging that number in, we get a point somewhere in here. I think it's 0.62. They thought it was 0.58. But anyway, it's going to come out to be about the same area either way. We can almost approximate that as a straight line. And the area under this curve is going to be the work done on the gas, I think. Nope, the volume is expanding. That's going to be the work done on the environment. If the arrow was pointing the other way, it would be the work done on the gas. But each of those squares has an area of 1 cubic meter times 0.1 times 10 to the 5th pascals. And if you count the number of squares, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and let's call it 16. So 16 times 10,000 is 160,000 joules. And the reason I am wrong this time is that the squares are not a whole meter wide, a whole cubic meter wide. They are only 0.5 meters wide. So we'll call that 0.5 meters cubed. So this is only 5,000 joules per square. So it's closer to maybe 88,000 joules. And they also said they counted 16, or they counted 17 boxes. I counted 16. So they said it was a little bit more than I said. And I finally had a chance to check my equation 22, and I found out that I had made a mistake. Indeed, when I was integrating, I meant to divide by 1 minus gamma, or I should have divided by 1 minus gamma, but I had multiplied. And so now I have got the correct formula. And you can see when I use this formula, not that part's wrong, but it comes out to be 83,250, which is, actually I should have plugged in 101,000 for the pressure, and I got 84,082. Or if I go ahead and round that, go ahead and use 101,300, all four significant digits, I get 84,332. So in the remarks, they say the exact answer obtained with calculus is 84,300 joules. So our result is a very good estimate. The answer is negative because the gas is expanding, doing positive work on the environment, thereby reducing its own internal energy. Question 12.6 asks, for an adiabatic expansion between two given volumes and an initial pressure, which gas does more work, a monatomic gas or a diatomic gas? So here's the two things we're comparing. Pressure equals C over V to the 5/3, and pressure equals C over V to the 7/5. And the one with the higher pressure, as you change the volume by the same amount, is going to win. So this one is C times V to the negative 1.67. I'll just say 1.67. That's 5/3 on the bottom. And this one is C times V to the negative 1.4. So it looks to me like the negative 1.4 is greater than the negative 1.67. So the diatomic gas is going to do more work because it's going to have a higher pressure for most of the time. Exercise 12.6 asks us to repeat the preceding calculations for an ideal diatomic gas expanding adiabatically from an initial volume of 0.5 meters squared to a final volume of 1.25 meters cubed, starting at a pressure of 101,000 pascals. So first we want to find P final, and then we're going to find a work using kind of diagram. So since P final, V final to the gamma is equal to P initial, V initial to the gamma, we can just divide by V final to the gamma here and combine those. So it's 101 kilopascals times V initial 0.5 divided by V final, which is 1.25, to the power of gamma, which is 5 plus 2 over 5, 7/5. The pressure comes out to be 28,000, so I'll draw a little PV diagram. I'm not going to be as careful with this one as they were. I'm just going to draw P and V. We're going to have, down here, we're going to have 0.5, and we're going to have 1.25. We're going to have something that looks like this, and it comes down like that. This pressure is going to be 101,101, and this will be 28. So I've drawn it not to scale, but we can see that we've got this rectangle and this triangle essentially. So you can see my scale is really bad. This is 28,000 pascals and this is 73,000 pascals. But the total area is going to be 0.75 times 28,000 plus 1/2 of 0.75 times 73,000. And now that gave me a result of about minus 48,000 joules. I'm sure if we'd calculated something in the middle here, it would have been way down. So we'd probably be subtracting all of that area in there, and we would end up with something more like minus 40,000 joules, which is what their answer was.